Hi, everybody. Today we are going to talk about the solution of linear systems, and especially we are going to talk about the elimination of method, which was offered by famous mathematician Gauss. That's why we sometimes call it Gaussian elimination method. So actually, before we pass to the elimination in this video, we are going to introduce elementary row operations. So let's first understand how it works. Suppose we have got a system, a linear system, any system of three variables. And we have here, you can see three equations and three variables. So any system we said that might have three types, three cases of solid. If it is linear, there can be three cases. Either the system has one solution, or it has got no solution, or it has got infinity many solutions. So we can see that each of these cases in our lectures. Today, I'm going to also revise the essence of elimination methods by elementary row operations. Elementary row operations. So first we start from understanding how it works. Before we pass to the process, we have to understand that we set up, in order for this purpose, we set up such a matrix which we call augmented matrix. So augmented matrix is the coefficient matrix which has got the coefficients of corresponding variables in the order that they appear. So x, y, z. So these are the coefficients of x. These are coefficients. This column will represent coefficients of y, and this column will represent the coefficients of z. So 1, -1, 1, and 1, 2, or 2. These are the coefficients and for corresponding system. But however, if we put here another limiting coefficients which are on the right side, sometimes we call them constant coefficients. If we add there this column, we get the so-called augmented matrix. So augmented matrix. So let's denote it by A star. And we are going to work on some issues related with augmented matrices. So let's first define what we can do with this. In order to understand it, let's first try to remember from our school time what we could do to equations. So in this equation, we can do some operations. Let's remember which were they. So first one, you can see in this system, we can interchange any equation. So we can change any equations here. First one with the third one or second one. We don't change actually the roots here. The solutions do not change. And also it doesn't affect the style of the system. So it doesn't matter the first one is this equation or the second equation. We don't change anything unless we don't change the coefficients. So we can interchange any rows. By the way, any times. So we can interchange them any times we want. So secondly, we know from our school years that we can multiply any equation by both sides of the equation by a number, by a scalar. It doesn't change the equation. So it doesn't mean that you multiply, for example, you can multiply the first equation here by 2, or you can divide by 3 or -3. That depends on our taste. We can do it. It doesn't change anything. So we can multiply any equation or any row, because we are talking about the rows, because rows represent the equations here. So the first row represents the first equation, the second row represents the second equation, the third one. When we change here, automatically the augmented matrix also change here. So we can multiply any row by a non-zero scalar. So we know that we can multiply by a non-zero scalar. Why non-zero? Because zero changes the essence of the equation dramatically. So it can change if we multiply both sides by 0. We can get a new system with different types of nature. So the third case is that when we multiply the system by a number, we can the equation by a number, we can add it to another equation. So seemingly looking at this augmented matrix, when we multiply any row here by any number, we can add it to the third one. So we can add a multiple of any row to another one. My suggestion here is that to learn these three operations, but do not mix it with determinant. Determinants also have the similar properties, the similar operations, but sometimes we can make their things difficult, and in some cases things change there. For example, we can multiply any row, but in this case the determinant value also multiplied by that number. Or maybe we can interchange any rows in determinant. In this case, you know, according to the property of determinant, -1 is taken outside. So when you change determinant's rows, interchange the rows, you get -1 in front of the determinant. So here we don't have this stuff, fortunately, so which helps us to solve. So again, let's accumulate what we have here. So we said that we have here in particular, three properties that we can apply, three operations. First, we can interchange any rows here, any equations here. So consequently, if we interchange these two rows here also change. Changing equations, position of equation changes the position of rows, but this doesn't affect, again, the solution process. So second one, we can multiply any row by a non-zero scalar. So we can multiply any equation by a non-zero scalar. So consequently, we can multiply any row in augmented matrix by this scalar. So we can multiply by 2, by 3, by 4, non-zero, and also we can multiply by 1 out of 2, by 1 out of 3 if you want to divide by something. And also the third case, we can add a multiple of any row to another one. So we can multiply, we know that we can multiply an equation by a number, add to another equation. We have done it, if you remember, we have done it at school. So we know it. So here also, we can multiply any row by the scalar and add to the other one. These three important operations, which are called elementary row operations, and which we use for solution of different systems, different linear systems. And we are going to also see an example where we are going to solve the problem using the elimination method. So I hope you enjoyed the video, and I'm going to introduce a new video right after it. So stay with us. Take care. Bye. See you.